Good afternoon. I'm Executive Associate Dean Per Peterson, and I'm delighted to be able to welcome Simon Segars, Chief Executive Officer of ARM Holdings, to Berkeley Engineering. Our Dean is also here. He just got back, so we're doubly represented, but it's a pleasure for me to be able to make this introduction. This is the first View from the Top program for this academic year, and it has been produced in partnership with the EECS Department Colloquium Series. These programs give the campus community a chance to hear from today's leading thinkers on technology innovation. They also showcase how engineering education is foundational to technology leadership. I'd like in particular to thank the Berkeley student chapter of the Institute of Electrical and Electronics Engineers, IEEE, yes, for co-sponsoring today's lecture. I'm also honored to welcome the alumni and members of our Dean Society who are joining us today. The loyalty and support of such friends play a key role in advancing the college's mission, which is to educate leaders, to create knowledge, and to serve society. Welcome to you all. Now I am delighted to introduce today's speaker, Simon Segars. He is the Chief Executive Officer of ARM Holdings, the semiconductor and software design company headquartered in Cambridge, England. He also serves on the board of directors. Under the banner of Architecture for a Digital World, ARM technology reaches about 80% of the people in the world, with chips based in its technology driving billions of products every day. In fact, I understand that ARM technology is playing a key role in our new design innovation curriculum here at Berkeley. In our interactive device design class, jointly taught by EECS and ME, and one of the first classes being held in our new Jacobs Hall, students are using ARM microcontroller boards to prototype novel wirelessly connected devices and products. They're using this technology to create medical devices in collaboration with UCSF, measurement devices for California's wine industry, energy and water-saving devices, and toys to teach programming and electronics. Simon Segars is the company's 16th employee and has held a variety of roles from junior engineer to leadership positions in engineering and business development. He led the development of early products that powered the first digital mobile phones, and he holds patents in the field of embedded CPU architectures. Simon is passionate about embedding energy-efficient IP wherever intelligence is required, and about using technology to empower people and businesses to improve outcomes for a globally connected population. He holds a bachelor's degree in electronic engineering from the University of Sussex and a master's in computer science from the University of Manchester. Please join me to give a warm Berkeley welcome to Simon Segars.
Thanks very much for that introduction, and let's be clicker. Great. Good afternoon, everyone. Thank you for coming today. It's my pleasure to be here. I get to speak to various audiences, but I don't get to come to a university very often and speak to people who might be inventing the stuff that's going to come next. I've been to Berkeley a couple of times over the years, actually helped sponsor a PhD project a long time ago now that was looking to implement an ARM core, and some good stuff came out of that. So great to be back here and have the opportunity to speak to you about what we're doing and our thoughts on how computing is evolving, how computing is changing the way in which we interact with each other, and how things are going to interact with other things, and just give some thoughts about where that future is going. So coming to a university, I thought, okay, well, so a long time since I went to university, sadly, but what did I learn when I went to university all those years ago? And I went to a class on computer science where I was told that all computers only had three things in them. They had a processor, they had memory, and they had some way of interfacing to the outside world. And I've got to say, I felt a little bit cheated at this point, because I thought when I came to university I was going to learn more fundamental things than just, there's only three elements to all computers. But this thought stuck with me as through my career in ARM. that although we can think about computers in different ways, ones with keyboards and screens and ones which don't have keyboards and screens, ones which are in our pockets, ones which are embedded, this statement that all computers have these three things has really remained true, and I think will remain the case. So the question is, if you've only got three things, it seems like there's limited ways in which you can put them together, but actually there are no end of ways in which you can build computers and how you can use them. And it's that I find really fascinating about what we do and about how technology in general is evolving. So, talking of computers, computers have changed quite a lot. When I left university, the IBM PC was a few years old, and I went to labs where there were racks of them on tables. Actually, there were PC clones that were very cheaply manufactured and didn't stand up to student abuse. But suddenly computers were becoming a lot more accessible. Prior to that, computers were kind of locked away in rooms. You had to have the right security badge to go play with them. And I had an internship through university where once upon a time they had mainframes, but they had a lot of mini computers as well. And so I got to play around with these things and experience all the different forms of computers. But computers were becoming a lot more personal. They were starting to move out of these back rooms onto the desk. But there were still really only things that were accessible when you were at work. And there were definitely something that was only accessible whilst you were sat down at a desk with a keyboard looking at a screen. Whether it was a remote terminal to the VAX or whether it was the PC itself, computing was something you did at a desk. Now, computing has changed. It's gone from black and white to a lot more colourful. And the way in which we interact with computers has obviously changed enormously. Computers are all around us. There's a large number of them being used in this room. Willing to bet you've all got a smartphone of some sort. And the way we're interacting with these things has completely changed. The cost of access to computing has changed enormously, and we can all now do computing without really realizing that we are using a computer. So computing isn't something that you do at a desk anymore. It's something that you're doing all the time, pretty much. It's around you, and that is going to continue to change in some really quite profound ways. So the interaction with computers changed a lot. So that's kind of computers that you touch, but as I said, computers are really going everywhere. They're going to be in your car, well, they are in your car. They're going to be in tiny sensors embedded in light bulbs, in security systems, in the road. There's a whole growth of embedded computing, which is in itself really quite fascinating. And computers are going into the home. We were having a conversation over lunch earlier about the interaction between all the electronic devices in your house, how they work with security systems, how they talk to each other or don't talk to each other. Computers really are everywhere, and computing is going everywhere. And this is what ARM is all about. We are about trying to embed computing anywhere we possibly can, because this idea of adding intelligence, we find really quite fascinating. If you can put intelligence into inert things which haven't necessarily need to be connected before, then I think that there's a huge potential for improving the way we live our lives and dealing with some of the challenges that society is going to face. So what do? We're very well known for having technology in mobile phones. As was mentioned in the intro there, I worked on a processor at a time when cell phones were turning into digital cell phones, and we had to solve this software problem of how do you put a high-performance 32-bit microprocessor into something with very low system cost. And the code size was too big, so we found a way of solving that problem. And as the company's grown, and as cell phones have grown, as smartphones have become a reality, then we're very well known for having our technology in these devices. But what do? We're often referred to as a semiconductor company. I find that a little irritating when we are, because we're not a semiconductor company. We design things that other people build chips out of. So if you were to take your smartphone apart, not something I necessarily recommend, but if you did, you'd see a whole load of chips in there. And if you take the main application processor and peel the lid off and have a look inside, again, you don't need to do this, others have done it for you, you'll see that modern application processors in smartphones are built up of lots of building blocks, high-performance processors, multi-core processors, graphics processors, video decoders, audio engines, lots of functional blocks are put together in these chips. And what our business is about is creating those IP building blocks, in trying to do them as best we possibly can, and then licensing them to companies that want to go build chips. And it isn't just the processor, it's some of those other IP blocks and some of the interconnect technology that you need to actually put a chip together. So we're trying to provide the building blocks to design, to verify, and then to physically implement some of these chips. And it goes beyond what's in the application processor, the main brain of your smartphone. If you were to look into the other chips that you see in a phone when you take it apart, there are microprocessors everywhere. I lose track of what the average number of processors per smartphone is, but it's quite a lot, between probably 5 and 10. The Wi-Fi, the Bluetooth, the touch screen, thumbprint sensor, there are all microprocessors behind there, running code, doing small amounts of work, taking some input, doing something with it, and making a decision. So the growth of embedded processors has been a fantastic factor driving our business. And as we've evolved, we've looked to create the technology that's needed in all these different areas. From a business model point of view, as I said, we don't manufacture chips. Our founding CEO is quite an outspoken guy. Used to say, we will build chips over his dead body. And he is still alive, and we still don't do it. It was a good idea then, and it's a good idea now, because building chips is really complex. But what we're trying to do is make the complexity and the cost of building chips a little bit simpler, a little bit less expensive. And if we can do that, then it makes the industry a bit more efficient, and people can spend R&D dollars doing things that really differentiate their end product. So we have a very long development cycle for our products. When we think about new processor architectures, we'll spend a few years simulating it and trying to optimize it, trying to get the best architecture. We'll then create a processor, which again takes a couple of years. We'll then license it to semiconductor companies. They'll build a chip out of that. That gets designed into a product. That then starts to sell. And so the lifetime of some piece of work that we do can be very, very long. One of the first processors I worked on back in the mid-90s is still selling today in very large numbers. You know, people ask, what is the lifetime of our product? Don't actually know yet. The company's only 25 years old. We haven't got enough data to work out what that average life is. So we're designing products, very long life cycle. We are licensing to chip companies. And when we started doing this seemed like a bit of a crazy idea. We would go to companies who were using embedded processors, and at the time, their embedded processors were their own. And we would say to them, it's a really good idea for you to stop doing that because we think it's a waste of money. Why don't you license it from us? And of course, most people would say, that's very interesting, go away. But we started to get some traction with this idea as cost and complexity went up and people were trying to put more and more functionality into a chip. This idea of licensing in some of the key building blocks really caught on. And there's some very good reasons for that. As we've increased the number of licensees, the number of people who want to do this, we've now got over 400 licensees of our technology. We're seeing our products used in all kind of end devices, from phones to TVs. We're in anti-lock brake systems in cars, DVD players, all sorts of end equipment. The volume of chips containing ARM technology has grown and grown and grown. Last year, our licensees sold 12 billion chips containing ARM processors. And when you add up cumulatively over the 25 years of the company, it's now over 60 billion chips have been built using our processors, which is something we're enormously proud of. Our business model works based on volume. We charge an upfront fee for access to our technology, and we get paid a very small royalty every time one of these chips gets sold. That adds up to a pretty reasonable business, and one where we find ourselves in the heart of many, many different end products and working with lots of people from across the technology industry. It's a really great and fun business to be in. Now, one of the other things that our founding CEO established as a priority for the business was that we weren't going to try and do everything ourselves. And it would be crazy to try and do so. And therefore, we were going to found this company on the principle of partnership. We're going to go out and work with people who would do things that we couldn't afford to do. They were going to do things that were going to enable them to grow a business, that were going to enable further industry efficiency as people look to build these ever increasing complexity chips. So we went out and we licensed the technology. We started talking to software companies who wrote development tools, operating systems, design tools, design services, applications. We just built up over the years this enormous ecosystem of partners that we work with, again, to try and make building an end product, which is horrendously complex, as simple as it possibly can be, and as low cost as it possibly can be. Again, over lunch earlier, we were talking about how, as consumers, it's great to go into Best Buy or Fry's or somewhere and just look at how cheap consumer electronics comes every year. And when you look at it, you're thinking, well, that's fantastic. You know, that big screen TV, I'll put it in my downstairs bathroom. You're not really thinking about what was the cost of all the R&D that went into building this. You don't think about, you know, a FinFET chip that's cost billions to develop, and how the cost of the consumer electronics is then ripples down the business. Well, as consumers, we love getting more stuff cheaper every year. As an industry, we've got to make sure that the cost of building it in the first place keeps getting lower and lower and is as efficient as it can be. Otherwise, you know, this industry breaks. So for us, partnership has been a big theme about that. We don't try and do it all ourselves. We celebrate this. We work with our partners and to share as much information as we possibly can. So cumulative 60+ billion chips is pretty good. You know, we're pretty proud of what we've achieved in the last 25 years. We're going to have our 25th anniversary in November. But you know, we're thinking a lot about what comes next. You know, what's going to enable the next 100 billion chips to get built using our technology, and how we're going to address the issues of complexity and cost and making sure that stuff seems to magically keep getting cheaper every year. Well, to do that, for our side, we're very focused on this energy-efficient technology. Although we started out with a big footprint into the mobile industry, we're focusing on system efficiency and low power. It turns out that those attributes, low power, low system cost, ease of design, ability to integrate with lots of other stuff, is useful in all sorts of other applications, whether it's the data center, whether it's the smallest microprocessor. Those features tend to be useful everywhere. So we are focused on building that portfolio of products that are going to enable people then to build chips. And through this partnership, do it in the most cost and energy efficient way possible, because that drives innovation. Anywhere where we see people just reinventing the wheel the whole time, doing work that doesn't actually differentiate the end product, you know, that for us is something that really, you know, there ought to be a better way of doing it. So we've been focused on the processor building blocks. We set up a not-for-profit 5 years ago to look at optimizing open source software for the ARM architecture. I was talking to an audience there. 500 engineers turned up on Monday to come and work on this, to ultimately give their products away, or give the result of their work away, to make system design, product design more effective. So through partnership, through our work around energy efficiency, we think that this can drive innovation that will ultimately lead to many more chips. So where are those chips going to be used? What I find really fascinating about the way embedded intelligence is really developing in different areas is how it's all kind of connected together. We anticipate continued innovation in mobile devices. The device you carry around with you today is phenomenal compared to 10 years ago. But we think there's a big requirement to keep improving the performance of the processor that's in your mobile device. The way you interact with it today hasn't changed a lot since the first smartphones. There's a keyboard. Voice recognition is getting better. You know, but the future of that, I think, is around more kind of a perceptual user interfaces, working out what it is you need when you need it, being able to talk to it, being able to gesture to it. Your device is going to need more and more computing power. And it's going to generate a lot of data, and it's going to consume a lot of data. We're going to see the growth of the Internet of Things. The Internet of Things is, I'll come back to this, is going to require billions of very small processors with sensors, with some form of connectivity connected to the network. And there are potentially going to be tens of billions of them, which have very different characteristics to that of a mobile phone. But they're all going onto the same network. And this kind of tidal wave of data that's going to go through the network is going to require an evolution of the network itself. I'll come back to that later on. Where's all that data going to? Where's it all coming from? Well, you know, the cloud has been a big feature of technology over the last few years. We used to call it data centers, now we call it the cloud. There's big growth in online computing that's going to store and process a lot of the data. But you know, the model that we have today, I think, is going to change as all of this evolves. We're big fans of wireless technology. Hate going into a conference room and seeing wires everywhere. It drives me crazy. So we want to get rid of all of that. But wired access, bringing broadband into offices, into university campuses, into the home, is another area where bandwidth is going to have to go up and up and up. And overall, what we're going to need to do over the next 5–10 years is deliver more data, faster bandwidth, with lower latency, to allow the interaction of all these systems to really give us the benefits that we want to see. So I'm going to dig into a few of these areas now. Let's start off talking about mobile a bit more. Love mobile devices. Seen smartphones go from relatively smart to really smart these days, and I think we're going to see them get even smarter. Relative to when I was at university and we were using this big clunky keyboard and monitor, I bet that your primary way of accessing the internet now is the thing that's in your pocket. I bet that if you left it at home in the morning, you'd go back and get it. Because we've just become very, very reliant on using this as a window into what is going on in the world. So smart mobile devices are getting smarter and smarter. They're going to get more and more sensors in them to interact with more and more devices around us. We're going to see the machines that we do use on our desktop get smarter and thinner and lighter and lower power. Lots of evolution in that direction. Lots of evolution, though, in the other direction as well. Wearable devices has been a bit of a kind of hype area over the last couple of years. But I think there's huge benefits that can come from wearable electronics. Whether it's smartwatches, I'm not wearing it right now, but I do have one and I use it every day. And again, when I leave it at home occasionally or the battery dies, it's a little bit irritating not to get texts and reminders pop up on my wrist. So I think there's a use model there that's really interesting. But in businesses, in hospitals, say, there are great benefits that can come from wearable devices. So we were talking a moment ago about access control to buildings. When I go to work, I have a card that I have to swipe to get in the building. Well, that seems a little bit Stone Age, really, given I'm carrying around a lot of electronics with me. Using wearable devices, using sensors that can track where I am, can lead to better safety in buildings. We were talking about nuclear power stations and how you monitor and maintain them. You know, there are lots of applications where being able to track people has big benefit. On the healthcare side, I think wearable devices have enormous benefits yet to come. If you go see your doctor, the first thing they're going to do is take your temperature, they're going to take your blood pressure, they're going to weigh you, and then based on these 3 data points and however it is you describe your symptoms, they're going to make some diagnosis. I'd much rather go to the doctor with a whole history of what's been going on in my body. You know, data tracked over time showing how my blood pressure has changed, how my weight has changed, how various other vital statistics about me have changed, coupled with data about my environment. Where have I been? You know, am I suffering from asthma because actually it turns out the air quality of where I've been has been really poor. You know, this is insight that comes from being able to track data that comes from wearable devices. Huge area, and I think we're only getting started on that. And it isn't just developed world, you know, first world problems that we can solve with this. I think there are many developing world issues that we can address with wearable devices too. Siri doesn't understand. She'll get there. We recently launched a project with UNICEF to try and encourage people to look at everything that's gone on with mobile devices and think about wearables and how they can solve problems for people in some of the poorest parts of the world. This is a competition that's been running. We're going to announce the winners of this later on. And looking at the stuff that's been submitted by people, it's amazing just the ideas people are coming up with for how to use all the benefits of mobile devices, mobile technology, wearables, cloud computing, how it all comes together, and how it's a great example of how just innovation has been unleashed through the benefits of all this technology. Now, wearables it kind of leverages off of mobile, but it's also a class of embedded computing. And I think the embedded space is really fascinating. When we think about computers, historically, it's how to make them go faster, how to make them do more quicker. Well, in embedded, you've got a different set of constraints. And I always think it's kind of fun to look back at one of the first, most famous embedded computers. This is, of course, the Apollo guidance computer, put the man on the moon, and was a great example of an embedded computer with a very limited interface that actually solved some really hard problems. It's interesting to think about the technology of this. This was built out of separate 3-input NOR gate chips, wire wrapped together. There's about 3,000 of them. They wire wrapped it. They kind of dipped it in some resin to stop the wires breaking, and then they sent it to the moon. I worry sometimes about the safety of my car. I'm not sure I'd want to bet my life on that, but clearly, fortunately, some people did, and they came home again. And so you think, well, computers get faster and faster. Actually, we're still building computers that have that kind of performance, but we're doing so now in a much more efficient way, and this is enabling us to put computers everywhere. So what's shown here on your left is one of the smallest microcontrollers that one of our licensee builds. This is a Cypress PSOC 4, very tiny microcontroller that has one of our smallest microprocessors in it. The processor itself on 40 nanometers is about the size of a human hair. It's absolutely tiny, but it has, roughly speaking, the same performance as that Apollo guidance computer. As you can see, it's a lot lighter and takes a millionth of the power. And because of that, because it's so low power, because it's so low cost, you can now use it to do things integrated with some other functions on this chip. Well, the options for what you can do there are pretty limitless. They really are limited by your ideas. This is one of the examples that it went into. If you've got one of these nice fancy black glass cooking stovetops in your house, there are little buttons on it that you can press. They're capacitive switches. Underneath that, you'll find a microcontroller reading what's on the sensor, making sense of it, ignoring the fact that you might have spilled some water over it and working out when it got pressed. Well, there's a microprocessor that does that, and it's this kind of microprocessor that is so cheap you can now embed it into the user interface of, in this case, a cooker. So an example of what's going on. We're still putting computers in space and moving on quite a long way from the initial Apollo guidance computer. Pretty soon, in about 80 days or so, there's a UK-based astronaut who's going to take a Raspberry Pi up to the International Space Station. Performance of which is massive compared to the Apollo guidance computer. I don't know what the ratio is, but obviously a lot. And they're going to use that to run some experiments. Just like here, hopefully the students at Berkeley are being inspired to go and invent things. To write the software that's going to run on this, to run the experiments, there's been a competition running in the UK to get school children to submit ideas for what's going to go up to space. The judging of that has happened. There's been coaches assigned to help people develop their ideas. Before the end of the year, I think this is going to get sent up to space. They're going to do a load of experiments. They're going to beam the results down to Earth. And hopefully this is going to inspire school kids to really get involved in computer science, because we're going to need more engineers in the future than we've got today. So this is one way that we're trying to stimulate some interest in technology. Embedded is just growing and growing and growing. The applications really are only limited, I believe, by human ingenuity. And compared to the cost of building that Apollo guidance computer, you can now get this for next to nothing. These are some examples of the development boards that you can now get for a few tens of dollars. You can plug them into your laptop. You can program them using free open source software development tools. You can hook it up to some cloud-based service and get as much compute power as you want for almost nothing, just a swipe of the credit card. And we are seeing innovation going on at the product level because of this accessibility to technology. This has never been cheaper. And as a result, we are starting to see innovation going on, utilizing all of this hardware to the point where you don't have to have a degree in electronic engineering to use one of these. If you're interested in putting a product together, and we're seeing all sorts of people using these devices, then it's as easy as it ever has been. We can make it easier, for sure. I mean, developing code is still quite hard, but for now we're in an environment that we've never seen before, and I think it's going to drive some really interesting innovation. Some of this is based on Linux, but we're seeing Windows running on a Raspberry Pi, Android, all sorts of different software environments running on these very cheap boards. And you can see, relative to the size of a dime there, some of these boards really are tiny. So very low cost, very low power, driving a lot of innovation. And this is going to be one of the factors that I think creates some of the use cases around the Internet of Things, or IoT. IoT, we really are in our infancy about what it's going to do. We'd like to show this picture just to kind of demonstrate the scale of what IoT can do, where it's going to be used. You can think about IoT in the house, you can think about smart security systems, the healthcare example I gave earlier, the kind of examples of IoT. But a lot of where IoT will be used and how it will deliver its benefit is going to be hidden to the average consumer. And I think that's a very good thing. IoT will be used to make energy delivery to your house more efficient. It will be used to enable transportation systems to become more efficient, enable us to move around ever-congested cities in an easier way. When you get stuck on the freeway, you think, why didn't my car tell me this? Why didn't it reroute it for me? Or if the train was late, why didn't that get pushed to me? Why can't I find out exactly when the train is going to turn up? Make some decisions about where I'm going to, how I'm going to get to work, how I'm going to get to class. So there are all sorts of examples where IoT can help. And when we think about how the population of the world's changing, how the middle class is growing, how more and more people are living in cities, how some developing countries are seeing huge population explosions, whilst at the same time in developing countries we have an aging population putting enormous strain on our healthcare systems, then being able to monitor people, data, work out when to water the field instead of just spraying it on and seeing most of the water evaporate, all of these things can be made more effective through the use of embedding sensors, embedding intelligence, and then processing data. So we are big believers that IoT is going to be a driver of technology and a really fascinating way in which we'll see technology evolve. So what are we going to need to make that a reality? IoT is going to have lots of these different endpoints, these sensors with the processor pulling off data somewhere. And the computers, they're all computers. They've all got some way of interfacing with the outside world, some memory, a processor, and some connectivity. What we're going to need for these is very different from the kind of computers that we've built historically. Historically, as I said, it was all about more, faster, get more processing power in it, more transistors, better memory, faster I/O. But for IoT, it's very different. It's about energy efficiency. It's about running something off a battery for years and years and years. It's about making it as small as possible so you can put it places that are just, you just don't see it there. It's just invisible. So we've got some real technology challenges to address to get big benefits out of IoT. One of which is just being able to operate at very low voltage. What's shown here on the right is a small device we put together. It's here. You can barely see it, which is why I've got it up there. It's a Bluetooth beacon. We've been trying to make Bluetooth radios as easy to put into a chip as any other building block. And what we got the engineers to do was just put together a very simple Bluetooth beacon as a demo. And this has got a small battery attached to it, can run for 10 years. So great energy efficiency, helped by the fact that the whole thing runs at 1 volt instead of 1.2 volts, which was the nominal operating voltage for the process. So we're kind of abusing the technology a bit to make it as good as it is. But we'd like to go much further on that. Don't want to run it at a volt. I'd rather run it at a few hundred millivolts. But manufacturing processes are really characterized around this kind of central operating point. They're well characterized there. And if you want to use them out of spec, well, really, you're on your own. And one of the ways in which we think we can make some of these devices simpler and more effective is to have some real work done on what happens when you do run processes at very low operating voltages. What is the trade-off between leakage and dynamic power? If you're operating down there, you can think differently about reliability because you're not driving as hard voltage swings through your transistors. So all different set of constraints when you're operating at that very low voltage that the technology answers aren't really there for at the moment. But we see this as a way that can really help make these devices simpler and better and run off batteries for a very, very long time. Now, one of the other key technologies that we need to build IoT devices is embedded flash. And there are many forms of embedded flash out there at the moment. But if you want to build something like this for next to nothing, they're still quite expensive. They require high voltages to run off. You don't really want to put a charge pump in something that small if you want it to run on a battery for, say, 100 years instead of 10 years. So whilst there's a lot of research going on, talking to our R&D guys, they keep saying to me, whenever you get the chance, tell people that just making something that's as good as current flash isn't kind of it. We need endurance to be thought about in a very different way because the life cycles of the products are completely different from putting a SSD in a data center somewhere. So embedded flash is one area where we're really hoping for some development in the technology so we can build these IoT devices. Integration is one of the other challenges that we face. Right now, if you want to put a processor with we've been able to integrate this radio, but there are lots of other radios you can't integrate on the same die. You're into trying to put different technologies together in a single package or on a really small substrate. And you can do it, but it's quite hard. It's not as easy as building a straight logic die on a mature process. So being able to integrate all these different technologies together, be it on a substrate or ideally within the same package, is an area of technology we think's got to evolve so we can put the intelligence, the radio, the sensors all together in as small and as low a cost a package as we could possibly imagine. So again, if you're doing some R&D, looking for a research project, please, I'll take one. Now, I mentioned about the side effect of IoT, the side effect of growing mobile devices is all the data that's going through the network. And the network is today, or the way in which client devices are connected to the cloud, is through a network that basically switches. It takes the address, works out where it's got to go, and somehow your packet ends up in the cloud, and somehow, magically, the answer comes back. Now, that's OK. That has served us well. But we think that this has got to evolve to enable us to have the bandwidth that we want, to enable us to have the latency, lower latency, which enable different services, different use cases, to enable us to deal with all the devices that are going to get connected to the network. The network's got to evolve. And we've seen over the last couple of years the migration from macro base stations to the combination of macro and small cells. Well, that's got to keep going. It isn't just about how many cells you've got. It's where you put the intelligence through the network. So we think the cloud's got to change to a much more distributed computing environment where all the processing isn't just up in a data center, but it's actually distributed through the network itself. And with different levels of computing, application acceleration, and storage, that is going to be the way in which we deal with this enormous amount of data that's going through the network up to the cloud and back again. It's basically, you want to put as little data up to the cloud as you can possibly get away with and process it along the way. And there are lots of applications for why you might want to do that. We're starting to see this happen. And there's a great example of one of the network operators, one of the, TV cable operators here in the US, who is starting to try and move the data closer to where it's going to get consumed. So if we all live on the same street and all decide to watch the same episode of Game of Thrones streamed from Netflix simultaneously, then right now there's a whole load of data coming down to all our houses. We watch it, we throw it away. That's very inefficient. So what this operator is trying to do is push the data much closer to where it is consumed and get the DVR out of your house and up to the end of the street. It's always struck me as quite crazy that everybody in my street having a DVR with a disk drive in their house storing exactly the same thing is just incredibly inefficient. You know, why can't you have a virtual DVR somewhere? Well, if you make it close to where data gets consumed, then you can get a lot more efficiency out of the network. So a big server box sitting at the end of your street with a whole load of the most popular content cached in it, and really, you know, your DVR just becomes a few lines in a database saying what you recorded. That's a lot more efficient, and that's starting to become a reality. So it only works, though, if you can build a network that's got a lot more intelligence in it. There are lots of other applications for this, IoT applications, filtering some of the data before it does get up into the cloud. And basically, the goal is to try and move from data to information. If you can work out the information that's in the data and just move that, then you get a lot more efficiency out of your network and out of your data center. So to make this a reality, we need a lot more silicon devices. Good news. We need a lot more silicon devices, a lot more embedded processors in them. Good news. And we're seeing many chip companies building different types of chip, integrating lots of processors, a few processors, storage functionality, functional acceleration, networking acceleration. All different types of chips are being built to solve that network problem. Now, networking is an example of, you know, we want more, faster, sooner, better. And how are we going to get that? Well, lots of technologies that we need. Some of them are well understood. You know, advanced process nodes. Everyone in the industry at the moment is thinking about 10 and 7 nanometer. I'm hoping one day EUV will turn up to make chip manufacturing a little easier. That would be good. We're seeing people integrate not just big microprocessors or clusters of microprocessors, but these accelerators in different forms, digital signal processors, FPGAs sitting alongside CPUs, give a very different programming environment. They're really hard to program, but once you can get a lot of efficiency out of the chip that you build. So this is relatively well understood, getting better all the time. You know, what do we need? Well, let's say these heterogeneous processors are hard to program, so you know, I really like to see the programming environment get a bit better. FinFET's great, but I learned earlier about some future transistors that are going to drive even lower voltages, which we're going to need to get the power out of the network, to get the power out of the data center. Getting all these chips talking to each other, hard problem, needs some evolution there, and again, stacking die together, getting the interconnect between them, hard problems. There are people who build them, but turning that into a mainstream set of technologies is what's really got to happen to enable us to get the real benefits out of everything I was describing. So, to sum up then, I think all of these different areas of computing have a long way to go in terms of development. I tend to talk to people who have a fairly dim view of how technology evolution is kind of capped out and your phone's as fast as it's ever going to be. Well, I don't think that is anywhere near the truth. There are lots of ways in which embedded intelligence, faster processors, more energy efficient processors are going to allow us to take data, get insight about what people are doing, get insight about what's going on in the world through these embedded things, this Internet of Things, and through all of that insight, enable us to lead better, easier lives, have more fun in our life, and generally lead to a more efficient use of the world's resources. So I believe that there's a long way to go with this. The reason I turn up to work every day is because delivering all of this is a lot of fun. We get to work with a huge number of people in the tech industry. And I hope in some way this has been interesting to you. And if you're a student here at Berkeley, you'll go and deliver on some of these technologies that my guys need to deliver all of those products. Thanks for your attention today.
Outstanding. Simon will now take questions. Let me note, we have microphones. It's important to use them. We have a packed house here, but also this will be broadcast on the web, and so to be able to hear the questions, that will be necessary. We're going to give preference to students in asking questions, so please tell us your name, year, and major. And questions.
Don't be shy.
Yeah, we have one in the back.
Yep.
Oh, he has it. Yep, come on. Yeah. Okay, yeah. Maybe later.
Hi, I'm Aditya. I'm a junior in the EECS major. I had a question about Internet of Things. So 10 years from now, do you see that Internet of Things will be more prevalent inside the home or outside in the public infrastructure?
I'd like to think it's more prevalent in some of the public infrastructure. I mean, I think that there's big benefits in managing energy, in managing, street lights is a great example. We're involved in a project to monitor street lighting in a number of cities around the US, and it's amazing how much money can be saved if you send the guy to fix the light bulb that you know's broken, rather than somebody rings up or there's a truck driving around looking for them. All of that is going to help lower just the amount of money that gets spent on delivering infrastructure. So I think there's big gains there, and I hope in 10 years' time we see IoT being used to solve a lot of those problems.
Hi, I'm Ardalan in the Mechanical Engineering Department, Master's Student Studying Controls. I was wondering, as more and more devices enter the Internet of Things, how do you guys address security issues as far as vulnerabilities?
Great, well, very good question. And as was seen with a recent example of the Jeep getting hacked whilst driving along, security in any system is very important, and it's an area where we've got a lot of work going on a number of fronts. One thing we're trying to do is create some end-to-end software to allow devices to be securely managed remotely. We've actually developed a small operating system that we're giving away, and into which you can incorporate encryption technology. So we've got some ideas about things you can do down in the hardware itself to look after keys and things like that. So you can start with some encrypted data and then create a secure link up to the cloud itself. Key thing about IoT, though, and I'm not going to say that we've got all the answers to this at all, there is an opportunity with IoT to get security right from the start. A lot of the reasons I think why we're facing a lot of security issues in kind of classic computing today is because it grew up in a world where connectivity wasn't really a thing. It was connectivity came later, and so we've been trying to fix security afterwards. And it's always hardest to put security on after you've built the thing. So we are sort of on a mission to try and get people to think about security from the start, and so hopefully it's a lot harder to penetrate some of these IoT systems. But hacking is going to happen. That is going to be a reality. We've got to work very hard to try and minimize the impact.
Hello. So I'm Chris. I'm a second-year PhD student in EECS. And I was curious you had mentioned integration of radios inside, on package with the processor. And I was curious, along with the baseband and all the necessary components, do you see the baseband as being incorporated into the processor as kind of more of an accelerated function, or do you think it truly should be a separate entity that is addressed more as an I/O function, so kind of an SDR versus a dedicated, system?
Yeah. So ideally, you try and incorporate that all into the one processor, and it really comes down to a trade-off around reliability, kind of real-time performance, and power. So SDR, lots of promise, and we put a lot of work into trying to build an SDR system a few years ago, and concluded that actually trying to do all of that in software was hard, and it wasn't very power efficient. So this is why historically people have kept it as a very optimized function. But with some of the, with IoT, I think there is the potential to look at that. Power is really going to matter. So it is that trade-off between having a dedicated function, you can use it and switch it off, it's highly optimized, but there's a cost associated with that, or from a baseband point of view anyway, doing it in the main processor. That's the trade-off.
Hi, I'm Sneheath. I'm a freshman in CS, and I just wanted to ask, what do you think is the next industry to be disrupted by technology?
All industries. I mean, it's amazing how your smartphone's a remote control for a cab driver these days. Who'd have thought of that? And what's really interesting about that is nobody was thinking about that when they were developing smartphones. Right? Smartphones being an open platform has enabled people with ideas to just go, oh, why don't I try this? And I'll use the cloud and I'll build this big business. And it's leading to a lot of disruption. I think, back to IoT, I think healthcare has huge potential for some disruption on that. To be able to use data in a more intelligent way about people, I think could potentially give rise to a lot of disruption there, a lot of wasted effort. So that, I don't know if this is the next one, but that is one area where I see huge potential, and I hope it happens, because one day, let's face it, we're all going to need it.
Last question right here. So at the beginning of the talk, I'm Nathan. I'm a second-year PhD student in EECS. The beginning of the talk, you talked about this spectrum of computing, from IoT down at these small little, human hair-sized CPUs, all the way up to the enterprise and the data center, and even high-performance computing. And so most of this talk talked about the IoT thing, and you talked a lot about integration and specialization in these processors. Do you see that trend of integration and specialization moving higher up that scale into the warehouse, into the data centers, into maybe even HPC?
Yeah, definitely. I didn't have time to include one of our great example we've got at the moment where that really does demonstrate that if you take an SoC approach to building chips for a data center, you can get a lot more efficiency out of it. So we have a number of our licensees who are doing this. They're integrating different acceleration engines with processors to try and solve some of the data center problems in different ways. And there's a white paper out written by PayPal who were looking at how you deal with doing fraud analytics in real time. So they're processing something like 3 million transactions a second, like 24/7, and they're trying to spot the bad ones. Their algorithms for doing that it was just too expensive, too power hungry to do it on a conventional server blade sitting in a data center. HP right now will sell you a box called Moonshot, and one of the chips that you can put in that has got a high-performance ARM CPU sitting next to a TI DSP. It's a chip built by TI, all integrated. So they have rewritten their algorithms to use that heterogeneous architecture, and they got an 85% reduction in the power for running this algorithm. So that's turned something that was too expensive to do into something that's actually feasible. And there's a white paper out there on this. It's really interesting. So yeah, taking an SoC approach from the smallest thing up to the biggest thing is a way, I think, in which we can get a lot more efficiency.
One more last question.
Hi, my name is Elena. I am a second-year PhD student in engineering education, and I am really excited about hearing how the Internet of Things and all these devices we can have to improve the quality of life of human beings. However, I cannot stop thinking what will happen with all these devices once they are going to be disposed of. Like, how about the amount of electronic waste we are going to have? So I'd like to know what's your approach to this subject.
Yeah, no, it's a very good question. I mean, with some of the IoT devices, hopefully they're going to be installed for a very long time. That, when you think about the amount of the Earth's resources that went into building it, you're actually getting a pretty good return on that. But in terms of a lot of electronic devices, frankly, we've got a long way to go in terms of recycling the electronics that's within them, dealing with batteries. I mean, there's a whole lot of noxious chemicals that are used in the production of semiconductors. But within the semi-industry, there is quite the push to green manufacturing. I mean, the industry gets this and is trying to do a better job of delivering all these benefits without creating a bigger problem than the one they're trying to solve in the first place. No magic answer on that, but I'm somewhat encouraged that as an industry, everybody does get it.
Thank you.
Great.
Simon, this has been an absolutely fascinating afternoon to spend with you. This concludes today's View from the Top, and please join me in thanking Simon for outstanding work. Thank you. And that's not all. Simon, I'm delighted to be able to present you with this small token of our appreciation.
Excellent.
You're now a Berkeley engineer.
Oh, well, wonderful. Thank you very much. Thank you. I'll wear that with you.